Hello everyone, so this is the GCSE Combined Science Trilogy, Physics Paper 1. This is the foundation tier that pupils sat in May 2019. I'm going to go through this paper and explain how I would have tackled it, and then in the description is a link to a blank copy of the paper and remark scheme, along with revision videos question by question if you need to go back and revise that content. So, question number 1 then. A designer made some shoes that have lights in them. Each shoe has a switch which closes when a person puts their foot on the floor. Figure 1 shows the circuit. What is component X? Is it a lamp, an LDR, or an LED? So we've got a switch in the bottom of a shoe. It's one of the shoes that just light up whenever your foot hits the ground. So this is obviously your battery or your cell. This would be your fixed resistor. Is asking about component X. This shape represents a diode, but you've got the two arrows coming off it. Those arrows represent light. So it is a light emitting diode, an LED. Complete the sentence then. When the switch is closed, the current in component X was blank the component in the resistor. Well, what you need to remember is current is the flow of electrons that go round a circuit. As the electrons flow round, they are delivering the charge to the component, which is the energy that it gives off. Now the electrons, the current, are not used up themselves. They are constantly just going round and round. It's like a flow of water. So therefore we would say the current in a circuit is the same as the resistor. Okay, so current in a series circuit is always the same. If it was a parallel circuit, it would be slightly different. But if you don't remember your series and parallel circuit rules, go back and watch the video. The designer tested how the number of cells affected the number of steps that could be taken before the light stopped working. Figure 2 shows the results. So you've got the number of cells that are in the shoe at the bottom, and you've got the number of steps in thousands. Determine how many more steps could be taken when the number of cells was increased from 3 to 5. Well, at 3, if we read off the graph, it's 900. At 5, if we read off the graph, it's 1500. So therefore the difference would just be 1500 minus 900 equals 600,000 steps. So question 1.4 then. How could the designer check the repeatability of the results? Could you repeat the experiment with a different resistor in the circuit? Could you repeat the experiment using exactly the same method, or repeat the experiment using different types of shoe? Well, if you're checking for repeatability, that means you keep everything the same. You do the whole experiment once, and then you do it again. Okay, so it would be the middle one. If you change something, either like by using a different resistor or by using different types of shoes, then you are checking, because you've changed something, the reproducibility of the experiment. But if you are repeating something, you are keeping everything exactly the same. When the potential difference across the resistor was 0.8 volts, the current in the resistor was 0.020 amps. Calculate the power. Now in the first half of a foundation paper, they're really nice and they give you the equations. So you've just got to substitute it in. Power is what we're figuring out. We know our potential difference is our voltage, which is 0.80 volts, times by the current, which is 0.020. Put that into your calculator, and that gives you a number of 0.016 watts, and that is your final answer. Literally substitute it, press the equals button on your calculator, and it gives you your answer. What other equation can be used to calculate power dissipated by a resistor? Okay, well, this is just a knowledge thing that you just need to know. Power can be calculated by current squared times resistance. Your three kind of key power equations are power equals current times voltage, or as it is above. Then you've also got power is energy divided by time. And you've also got power equals I squared times resistance. So that is just knowing your equations. Question 1.7 then. What happens to the temperature of a resistor when there is a current in it? So what happens to the temperature? Well, think of any circuit. The more happens, the more current that you put into a circuit, generally they get hotter. So it would say the temperature increases. There is a current of 0.02 amps in the resistor for 180 seconds. Calculate the charge flow. Again, it's given you the equation here. It's told you the current is 0.020 and the time is 180 seconds. Be careful because sometimes they put it in minutes, but here they've been kind again. So you literally just have to substitute it and it gives you an answer of 3.6 coulombs. So that's a nice, easy question to start off with. Question 2 then. A student investigated how the area of a solar panel affected the output potential difference of the solar panel. The student placed different sized solar panels under a lamp, and it shows a picture of a solar panel under a lamp. Which variables should be controlled? Well, it says that they are changing their independent variable. What they are changing is how the area of a solar panel affected the output. So that is their independent variable. So what is going to be their control variables, which they keep the same? So the area of the solar panels, that is the independent variable, as we just said. The brightness of the lamp, well, that would be quite important. It's not the bottom one, because that is the dependent variable. That's what they're measuring. So it would be the brightness of the lamp is what they should keep the same. Question 2.2. The student measured the output potential difference using a voltmeter. When the voltmeter was not connected, the reading on the voltmeter was 0.7 volts. What is the name given to this type of error? Well, it would be a zero error. A zero error is when your measuring device is not starting at zero. It's like getting on a pair of scales and measuring your weight or your mass, but it's not at zero. So therefore, the actual measurement is going to be off. Table 1 shows the results of the investigation. The readings for which solar panel show an anomalous result. Now, an anomalous result is one that doesn't fit the pattern. So as you can see, solar panel A, they're all consistent, they're all relatively close together, as are solar panel B. But on solar panel C, we've got two that are the same, but we've got one that is significantly different. So we would say that C is the one with the anomaly, and again, D, they're all the same, no anomaly there. The student did not have a solar panel with an area of 40 centimeters squared. Determine the most likely value for the mean potential difference of a 40 centimeter squared solar cell. So this is only a 1 mark question, so it's a bit of a logic question. Don't overthink it. Look at your mean values. It goes from 2.5 to 5 up to 7.5, and then you can see there's a gap where 40 should be. Now, if it was 40, it would be the number that is halfway between 7.5 and 12.5, which would just be 10. So you would expect 40 to be 10 volts. The total input energy transfer into one of the solar panels was 0.8 joules. The useful output energy transfer was 0.96 joules. Calculate the efficiency. Where again, they've been kind and given you the equation here. So the useful output from the question, reading it carefully, was 0.96. The total input energy was 8.0. So again, I just substitute it. 0.96 divided by 8.0 is just 0.12 if you do that on your calculator. Sometimes it might ask you to put it into a percentage when you would times it by 1,000, but it hasn't here, so you literally just leave it as 0.12. It then says, solar power is a renewable energy resource. Complete the sentence. A renewable energy resource is one that is blank as it is used. Well, if it is renewable, we don't tend to burn renewable energy, unless it's possibly biomass, but we don't really do that. Consumed, we don't really consume wind, we just utilise it. To make it renewable, this is the whole point of non-renewable versus non-renewable, is that we can replenish renewable energy, but we can't replenish non-renewable energy. Question 2.7. Some homes have solar panels which generate electricity. On a sunny day, the potential difference across a solar panel is 31 volts. A charge of 490 coulombs flows through a solar panel. Calculate the energy transferred. And it's given you the equation, but you've got to give it two significant figures. Now, this one is worth an extra mark compared to the other calculations that we've done. So therefore, what it says here, give your answer to two significant figures, is where that extra mark is coming from. But they've given you the equation. So our energy transferred is our charge. Now charge is measured in coulombs, so it's 490 times by the potential difference, which is 31. So 490 times 31 gives you 15,190. Now this has asked for it to two significant figures. So if you draw your line after two figures, we can see that the next number is a 1. Because it is a 1, we round down, so therefore we would just change it to 15,000. If you put 15,190, you would get 2 marks, but if you put 15,000, you'd get 3 marks because you did this extra step of putting it to two significant figures. Question 2.8 then. Why do solar panels on homes help reduce the environmental impact using electrical devices? So solar panels obviously make electricity, okay, and cause a current to flow. So what is the advantage of using it? Less electricity is used in the home. Well, just because you've got solar panels doesn't mean you're going to be using less electricity. They just supply more of it. Less fossil fuel is burned. Well, potentially. The electricity from solar panels is cheaper. Solar panel energy is not cheap at the moment. So therefore it must be the second one. Less fossil fuel is burned. Generally at the moment, most of the energy in the UK comes from gas. We're burning that gas, which is releasing CO2 in the atmosphere. If we've all got solar panels, it would mean that less CO2 from burning gas would be produced. Question 3 then. In an experiment, a beam of alpha particles was directed at a thin sheet of gold. Most of the alpha particles pass straight through the gold. Alpha particles, which pass close to the nucleus of a gold atom, did not pass straight through. What happened to the alpha particles which pass close to the nucleus of a gold atom? So this is our atom, this is our nucleus in the middle. Now this was the experiment that Rutherford did. He fired alpha particles at a gold nucleus. Most of them passed straight through, but the ones that came close to the nucleus were either deflected, or if they hit it bang on, they would have then been reflected. So you could say either of those two words, reflected or deflected. That's all because all the mass is in the centre of the atom and the positive alpha particles repelled away from the positive nucleus. Question 3.2. The results suggested that the diameter of the nucleus of a gold atom was 1/6000 of the diameter of the atom. The diameter of a gold atom is 0.18 nanometers. Calculate the diameter of a gold nucleus in nanometers. Well, if it's told you the diameter of the whole atom was 0.18, that is the diameter of the atom, and it's told you the nucleus is 1/6000, so 6,000 times smaller, you would then just do 0.18 divided by 6,000, which equals 0.000030. Okay, it's only a 2 marker. They've only so it's not going to be too complex, and they've given you two numbers in it, so you just need to recognise that you just need to divide it, because it's 1 over 6,000, 6,000 times smaller. Further experiments showed that the gold nuclei are surrounded by electrons in different energy levels. So they then found the nucleus, and we know this, the electrons are in shells. Figure 4 shows 3 of the energy levels around the nucleus of an atom. So you've got A, B and C. The electron in energy level B absorbs electromagnetic radiation. What will the energy level, which energy level will the electron be in after it has absorbed the electromagnetic radiation? Tick one box. Well, if it's absorbing radiation, it's going to gain more energy. Okay, so absorb, mean it would gain energy. If it was releasing energy, it would lose the energy. So because it's absorbing it, the electron goes up to the higher shell, or the higher energy level. If the energy is then released, it would then go back down to where it is. Okay, so the key thing to remember is when you absorb energy, or if electrons absorb energy, they go up the shells. If they release energy, they go down the shells, okay, towards the nucleus. Figure 5 shows how the temperature of a small sample of gold changes as it's heated from a solid to a liquid. What is the melting point of gold? So what's happening in this graph is that we're heating up the gold, it's getting hotter and hotter, okay? But in this part of the graph, it is still solid, it's just getting warmer. When you get a flat line, that means you've got a change of state. So the melting point is the point at which on this graph, the line goes flat. Now, the difficult part on this question is identifying the scale. So you've got 10 little squares that show a difference of 250. So if you've got 250 divided by 10, that means that each little square is worth 25. Reading off the graph, we can see it's gone up 4 little squares above 1,000. If each little square is worth 25, that would take us to 1,100. So 1,100, 1,100, 1,025, 1,050, 1,075, 1,100. And that would be your melting point. How many minutes did it take for all of the gold in the sample to change from a solid to a liquid? So if we have a quick look at the time axis this time, well, it started melting at 4 minutes and it finished melting at 12 minutes. Therefore, the difference would just be 8 minutes. Subtract 4 from 12 to give you 8. What does the gradient of the graph represent? Does it represent the internal energy of the gold? Well, energy is measured in joules. This graph had temperature in degrees Celsius and time. It doesn't have any units to do with joules, so therefore it's not about energy. Therefore, because it's not about energy, it can't be the specific heat capacity, because the specific heat capacity of a substance is the amount of energy needed to heat 1 kilogram of material by 1 degree Celsius. So it can't be that. So therefore, what this graph is actually telling us is the rate of change of the temperature of gold. That is what the axes tell us. Therefore, that is what it is telling us about. Question 4 then. Protactinium is radioactive. One atom of one isotope of protactinium contains 91 protons and 143 neutrons. What is the correct symbol of this atom? So in order to do this, we need to remember our atomic number is our number of protons. So 91 from the question would go at the bottom. Now the top number is our mass number, which is the number of protons and neutrons added together. I've got 91 protons and 143 neutrons. If I add that together, that makes 234. So therefore my answer would be the second one, as that matches. A student investigated how the count rate from a sample of protactinium changed over time. Table 2 shows the results. So you've got time going up in every 50 seconds, and you've got the count rate going down. Figure 6 shows some of the teacher's results. Complete the graph in figure 6. Use data from table 2. So I can see they've plotted at 0, 50 and 100. So those ones are done. So I need to do 150, 200, 250. So tick off the ones that they've done. So we've got to do 150 is 45 and 200 is 27. So just make a little note to myself, 45 and 27. So 150. Now this scale, you've got 10 squares and you've got a change of 50. Therefore, each little square is representing 5. So therefore, at 150, it would just be one little square below 50. And then at 200, that would then be 27, which is half, just above 25, which is halfway. Okay, just double checking. Yep, it's just 150 and 200. So you only need to plot 2 points. And then we need to draw our line of best fit. Again, remember, don't be afraid to change and move the graph paper to make it easier for you. You should see you've got a curved line of best fit, which we can keep extending if we need to. How much time did it take for the count rate to change from 200 counts per second to 100? So we can then use our graph. We go along at 100 and then we can go down. Okay, now I've got, again, this would be going up in a scale of 5. I've got it 4 squares along, so that would give me 70 seconds. So 50, 55, 60, 65, 70. Oh, I think I missed a question. Question 4.4. What is the half-life of protactinium? Well, the half-life of protactinium is the time it takes for half of the radioactivity to go, or the time it takes for half of the isotope to become stable. So it's gone from 200 down to 100, and we've already just read off what happens at 100, and we see it takes 70 seconds. So therefore, our half-life is only 1 mark, so therefore it's telling you, it's probably an easy question as well, is 70 seconds again. Question 4.5. The nuclear radiation from protactinium can pass through paper. The radiation, though, can only be detected up to 1 meter away from protactinium. What type of radiation is emitted by protactinium? So this question is assessing what we know about the 3 different types of radiation, alpha, beta and gamma. Now alpha, we should remember, is stopped by paper. Beta is stopped by aluminium. And gamma, well, the only thing it's stopped by is thick lead. And it is a wave which can travel very long distances. Now, this is telling us in the question that protactinium can pass through paper, so it can't be alpha, because otherwise it would be stopped by it. But it can only be detected up to 1 meter away. Gamma, because it is a wave, can travel a huge distance, so therefore it's not gamma. A neutron is not a type of radiation, so therefore, process of elimination, it must be beta. The teacher read an article about the effects of radiation on the human body. Why are articles in scientific journals generally more trustworthy than articles in newspapers? Well, the whole thing about scientific journals, and this is the phrase you need to use whenever you see a question about a scientific journal, is that everything that goes into them are peer-reviewed, which basically means any claims or any discoveries are checked are reproduced by other scientists to make sure that they are accurate and the data they've collected is trustworthy. Question 5 then, it shows a toaster. The toaster is connected to the main supply using a 3-core cable. What is the function of the earth wire inside the cable? To carry the current from the supply to the toaster, well, that carrying the electrical charge and current in, that is the job of the live wire, so it's not that. To complete the circuit in the toaster, no, it's not that. To melt if a fault occurs inside the toaster, well, that's the job of the fuse. Okay, the fuse is the little device that melts inside the plug if too much current occurs, or to stop the metal case of the toaster becoming live if a fault occurs. It is that. So an earth wire only generally actually exists on components that have metal casing, because if the live wire does come loose and touches a plastic material, it's not going to be a danger. It only becomes an issue if the live wire touches a metal case. Then in this situation, this whole toaster can become a potential hazard of a massive electric shock for a person. Complete the sentences. Choose answers from the box below, and you've got the different colours. The insulation around the earth wire is green and yellow. It's the striped wire. The insulation around the live wire is now brown, and the insulation around the neutral wire is blue. Okay, if you don't know how to wire a plug, make sure you watch the little revision video attached. A toaster is switched on for 120 seconds. The power of the toaster is 850 watts. Calculate the energy transferred by the toaster. It's only 2 marks, so again, don't overthink it. It's asking you for energy transferred, power times time. Your power is 850. Your time, they've given it to you in seconds, is 120. So 850 times by 120 is 102,000 joules. That's an easy 2 marks. Complete the sentences. When the bread is lowered into the toaster, a spring is stretched. The stretched spring stores what type of energy? So you've got chemical, elastic, kinetic, thermal. Thermal is heat, kinetic is movement, elastic, well, we know that what that is, and chemical tends to be in obviously chemicals, but also food. So the stretched spring would obviously contain elastic potential energy. As the bread is toasted, the spring makes the toast move upwards. The speed of the toast increases. The blank energy of the toast increases. So as your toast is being shot up out of the toaster, it would then be moving. So it would be the kinetic energy of the toast increases. Question 5.5 then. So this is reaching the part of the paper where they're not going to give you the equations. This is when it's testing to see if you've actually learnt them. It says write the equation that links gravitational field strength, gravitational potential energy, height and mass. Now the equation is gravitational potential energy equals mass times by height times by gravitational field strength. Okay. Question 5.6. The toast was moved upwards by the spring. The change in GPE was 0.049. The mass of the toast was 0.05 kilograms and the gravitational field strength was 9.8 Newton kilograms. Calculate the change in height of the toast, and this is worth 3 marks. So in this situation then, you've had to know the equation, and there's going to be quite a complex equation to use because it is worth 3 marks. The equation that you should have known from up here, you've got to rearrange it to help you get the height. So you want the height to be the subject of the equation. So you can substitute in what you know already. If I just write it again, GPE is mass times height times gravitational field strength. And that's the way you should learn it. You've been told your GPE is 0.049 joules. Your mass is 0.050, your height is your unknown, and your gravitational field strength is 9.8. So if I rearrange the equation, what I have to do is make the question mark the subject of the equation. So I can do the inverse, I can do the opposite to the other parts on that side. So I don't want to be timesing by 0.05 or times it by 0.9. I can divide by both of them. Okay, so divide by 0.05 times by 9.8 both sides. So that tells me my equation should then be 0.049 divided by 0.05 times by 9.8. That then would equal my height, which is my question mark. So I've just rearranged the equation, making sure I'm dividing it. Okay, and that would then give me an answer of 0.1 meters. Question 6 then. A student investigated how the current in a resistor varies with the potential difference across the resistor. Figure 8 shows part of the circuit used. The student connected an ammeter and voltmeter into a circuit. What is the correct way to connect an ammeter and a voltmeter into the circuit? So, with an ammeter, which measures your current, what you should always do is make sure it's connected in series. It's in the same branch as the component. With a voltmeter, which is measuring your voltage or potential difference, we always make a little circuit, a little branch that goes across the component, because you're measuring the change in the potential difference, the change in the pushing force. So therefore, we say it's attached in parallel. So ammeters are in series, voltmeters are in parallel. So therefore, using that information, it will be the third one, in series with a resistor for an ammeter and a voltmeter in parallel. The student increased the resistance of the variable resistor. How did increasing the resistance affect the current in a circuit? So your current is your flow of electrons going round and round. The resistance is the opposing force trying to slow them down. If you are increasing the resistance, then therefore you would be slowing or reducing the current, because you're making it harder for those electrons to go round the circuit. Question 6.3. How should the student change the circuit to give negative values for current and potential difference? Well, you might remember when you've used a voltmeter or a ammeter that the numbers are normally 0.00 or 0.01 or 0.02. To get negative readings, what you do is simply reverse the components. Okay, so you would reverse the battery and then it would be minus 0.01 or minus 0.02. So your answer would just be reverse, to be honest, you could just reverse the cell itself, so therefore the current would just go in the opposite direction. Name the type of relationship between current and potential difference for a resistor at a constant temperature. So this is one of the voltage current graphs you need to know, and that is if you've got voltage and you've got current, if one doubles, the other doubles. So you would say it is directly proportional. Write the equation that links current, potential difference and resistance. So potential difference, remember, is your other word for voltage. So it's V equals I times R, which is just one of the equations you need to know. The current in the resistor was 0.12 amps when the potential difference was 3 volts. Calculate the resistance. So if you put that into a triangle, V equals I times R. So R is voltage divided by current. Your voltage is 3, your current is 0.12. So if you reverse that and divide it, it would give you a resistance of 25 ohms. Question 7 then. A scientist cooled the air in a container. The temperature of the air changed from 20 degrees to 0 degrees. The volume of the container of the air stayed the same. Explain how the motion of the air particles causes the pressure in the container to change as the temperature is decreased. So, if you are reducing the temperature, think about what that is doing to the particles. If you are reducing the temperature, that means they are going to lose their energy and they are going to go slower. So you could start off by saying the particles have less energy, and because they have less energy, they would be moving slower. The particles move slower, or you could say less kinetic energy. So therefore, because of that, they would have fewer collisions with the walls of the container, therefore reducing the pressure. If you think what you can do to increase the gas pressure is to heat it up, and therefore the particles move faster and therefore you get more collisions, well, this is just what is happening in reverse, cooling it down so there's less collisions, so the pressure goes down. The air contained water that froze at 0 degrees. The change in the internal energy of the water as it froze was 0.7 kilojoules. The specific latent heat of fusion of water is 330 kilojoules per kilogram. Calculate the mass of ice produced. Use the physics equation sheet. So if it says use the physics equation sheet, it's one of the equations you haven't had to learn, so therefore it will be on the sheet. So the energy equals mass times by specific latent heat, and that will be on your equation sheet, so you just copy it down. You can then substitute. Your energy is 0.7 kilojoules, your mass is your unknown, and your specific latent heat is 330. Rearranging the equation, I'll just do the opposite or the inverse to get mass as the subject of the equation. So 0.70 divided by 330 equals the question mark. So doing 0.70 divided by 330 gives you an answer of 0.0021 kilograms. Doesn't say anything about significant figures or decimal places, so you can just leave it at that. Question 7.3 then. The air also contained oxygen, nitrogen, and carbon dioxide. It tells you the different melting points and boiling points of these different gases. It said the scientists continued to cool the air to a temperature of minus 190. What is the state of each substance at minus 190? So therefore, you've got to look at the melting and the boiling points and then figure out what state it's in. Now, the easiest way to do this, I think, is to draw a line on your graph of paper and label the melting point and the boiling point. Just helps you visualize it, okay? And you can do it for each of the gases. Now, if you're below the melting point, it will be a solid. If you're between the melting and boiling point, it will be a liquid. And if you're above the boiling point, it will be a gas. So if we look at oxygen, okay, we know it boils at negative 183. So negative 183. It freezes, so its melting point is negative 218. So where does negative 190 fit into this? Well, it's lower than negative 183. It'd be around here. Negative 190. It's between your melting and your boiling point, so therefore it would be a liquid. It says nitrogen, so do a different line. It says nitrogen boils at 195 and it freezes at negative 210. So where is 190? Well, it's lower than 195. So therefore, as it's this side, to the right of the boiling point, it would be a gas. And then carbon dioxide, it said it sublimates at -78. So sublimate means it skips the liquid stage and it would go straight from a gas to a solid. So sublimate, you should remember, is when it just goes from a solid to gas or gas to solid. So the last question on this paper then, 7.4. The air also contained a small amount of argon. As the temperature of the air decreased from 20 to -190 degrees, the argon changed from a gas to a liquid, to a solid. Explain the changes in the arrangement and the movement of the particles of the argon as the temperature of the air decreased. So it's basically saying it started off as a gas, then it turned into a liquid, then it turned into a solid. Explain the changes in the arrangement and movement of these different stages. So when it was a gas then, what do we know about gases? Well, we know that as a gas, the particles move freely and fast. They have a low density. Okay. Now, as they cool down, they lose energy and become slower, as we just said on that gas pressure question. Now, as they lose the energy, the particles will eventually condense into a liquid. The particles lose energy and condense into a liquid. Now, in a liquid, the forces of attraction are stronger than in a gas, but in a liquid we know the particles can still flow They are in an irregular structure, okay, allowing the movement, and it's still a random motion. Okay, they continue to lose energy, and as they continue to lose energy, eventually they will freeze. Okay, now that is when it turns into a solid, and we know that in a solid, the particles are arranged in a regular way. Or regular structure. They cannot move or flow. They have a high density. Okay, and you can also say, although they cannot move, they can only vibrate. And again, there is a much less kinetic energy and higher or much stronger forces of attraction. Stronger forces of attraction. So all we have basically done is broken down the properties of a liquid, a gas and a solid as it's lost temperature, but we're making sure we include the reasons why in terms of energy and forces of attraction. Okay, so making sure we link in those parts. Now, that would be enough to probably get you 6 marks on that question. Hope this paper was useful. Make sure you go back and look at any parts of the revision videos if you're not sure on any topic. And make sure to have a look at the other walkthroughs if you found it useful. Thank you very much.